Hi, welcome back. In this lecture I want to talk about the kernel trick. This is a technique that we're going to use for the quantum version of our support vector machine. So it's a quite important lecture for us. So far we have seen a vanilla support vector machine that can be only trained by finding linear separation between data elements. And the main assumption we had is that given a data set, we can separate into classes our data set by finding an upper plane. However, the reality and the dataset, real-world dataset, are quite different, are not always linearly separable. So, for instance, the data shown on the figure on the right here cannot be effectively separated by any support vector machine. There is no line that we can draw on this diagram to separate the orange and the blue line. In fact, we will need two lines to do it. That will be not possible in a vanilla support vector machine. What we are going to do? So we're going to do, in order to deal with data set with two classes that are not linearly separable, we're going to introduce the kernel trick. The kernel trick addresses the problem of non-linearly separable data set. And what this method does? Well, this method basically maps the data from its originally space. So typically we have this space, x1 and x2. These are 2 points. And we're going to use a map or a function phi to map to a different space. So the dimension of these two display space can be different, and lowercase and uppercase. And the higher dimensional space is typically this classical feature space. The higher dimensional space is known as the feature space. And this function phi is called the feature map. So instead of doing the classification directly in the original space, we apply a feature map or this function phi, and we go to a space with a higher dimension. And this phi is called the feature map. We're going to use feature maps in quantum machine learning technique, for instance, quantum neural networks. So it's very important that we understand these concepts of feature map. So how this is going to work? I'm going to show you a very nice example building on the first slides of this lecture. So we go to the right top of these slides and you see this data set is not linearly separable, but if apply this feature map fx and we increase the size, so we go from 1 dimension to 2 dimension, and we calculate the first coordinate as x and the second coordinate x square, we obtain this higher dimensional data set. Note that now we are in a position of be able to separate two different classes, the orange and the blue. After this, there is an hyperplane that perfectly separates the two categories. In the previous pair of lectures, particularly the last one, we saw that the training of an SVD boils down to calculate an inner product between xj and x. So to train an SVM and to classify new data on a feature space with a feature map phi, we need to compute scalar products on it of elements returned by the feature map. And as we saw in the previous lecture, this is because during the whole training process, the only operation that depends on xj points is an inner product, the inner product that we see here when classifying a new point x. If instead of xj we had the phi of xj, that is our feature map applied to the data point, we just need to know how to compute this inner product of the feature map of the different xj and xk point. And this is an operation that we can do in the feature space. The function defined by the inner product of this value that come from the feature map is called the kernel function. So kernel function are functions that can be represented as an inner product in some space. Let me see, this is an inner product. What is important for us that in the training and in the classification of SVD, we can act directly in the feature space, and the inner product is the single and only computation that we need to perform in the feature space. This is the last slides. Talk to you soon.